may also know about the ETSI masks, which to a degree also serve as a parameter that says how well antennas perform in terms of noise. Let's have a look at those. It is important to clarify that ETSI masks consider two main cuts of antenna radiation pattern, the azimuth and elevation. They consider two slices of the 3D radiation pattern, so again, rather completely incomplete, so to say, measure from the point of view of the whole 3D radiation pattern, all the side lobes that matter in WISP networks.
So he's saying that ETSI masks are incomplete because they only consider the azimuth cut and the elevation cut. And I guess he's saying that you should consider the entire 3D radiation pattern. This is a little strange to me because he's arguing that having two-dimensional cuts is not complete and that you need to account for the 3D pattern. But having two-dimensional cuts is understanding the radiation pattern in 3 dimensions. These two cuts are the most useful. So the azimuth cut lets you understand what that beam is going to look like on the azimuth plane, which is the horizon. It also lets you understand how to position your antennas with other antennas in the same ring of the tower, the same elevation on the tower, to position the antennas within the other antenna's nulls. The azimuth cut is very useful. Similarly, the elevation cut lets you understand what that beam is going to look like in front of the antenna, the beam propagation on the elevation plane. It also lets you understand how it's going to interact with co-located antennas above and below. So these two cuts are very useful. In RF Elements datasheets, they also just show you the azimuth cut and the elevation cut. This is the Ultra Dish 29. That's also true for the Ultra Horn. They just show the azimuth pattern and the elevation pattern. A 3D radiation pattern isn't necessarily useful. What you need is detailed information to use. And the basic problem with beam efficiency is it's just not useful. You can't do anything with it. It's not that it's incomplete, it's just not useful.
ETSI masks are observed at 3 frequency points, so an improvement, the beginning, the middle, and the end of the spectrum an antenna works in. Nevertheless, the rest of the spectrum, which is rather wide in the case of WISP networks, is
saying that the ETSI mask only consider 3 frequency points: the beginning, the middle, and the end. RF Elements datasheets only show you 1 frequency point, 5.6. This is the Ultra Dish. This is supposed to be a wideband antenna operating from 4.9 to 7.1. They arbitrarily chose 5.6 as the frequency point. But with antenna patterns, they're most likely to fall apart on the edges. That's where you're most likely to have problems with the radiation pattern, with side lobes manifesting. You want to see the edge cases. You don't want to see a cherry-picked value with a hand-drawn antenna pattern. You want to see a detailed antenna pattern, and yet it is helpful to see an antenna pattern at the beginning of the frequency range, at the end of the frequency range, and then it is helpful to have the ETSI mask to let you know how that antenna pattern looks relative to industry standards. This is Cyber Antennas Class 2 dish. The Class 2 is conforming with ETSI standards, and we have 5.1 gigahertz, 5.6 gigahertz, 6.0 gigahertz, 6.8 gigahertz, and 7.125 gigahertz. So that's 5 different frequency points, and then we show the ETSI mask on each one of them. We have vertical and horizontal polarizations. So you get an incredible amount of detail, and this is the detail that WISPs need to to understand how to use our antennas. This is not beam efficiency, a single number representing the amount of side lobes on an antenna is also not a useful antenna parameter.
Included in ETSI mask's definition. So again, not very robust measure. So how does one get to the ETSI masks and how do they look like? Starting with the polar plot, you may know from the antenna datasheets, we're drawing it on an XY axis or XY plot. ETSI masks are the blue dashed line, which says that the radiation pattern should stay below the mask so that an antenna can be declared compliant with a given ETSI norm.
If this is a 30 dBi antenna, then 30 dBi would be centered at 0 degrees. So it's normalized to 0 degrees. And this black line represents the signal levels at any angle relative to the center of the beam. So at 90 degrees here, you can see that's at about negative 25 dBi. So negative 25 dBi from 30 dBi. So it's at about 5 dBi. And it's functioning like a 5 dBi antenna at 90 degrees. When you're perpendicular to the antenna, it's functioning like a 5 dBi antenna. And that's what this chart represents. The ETSI mask is this blue line here. You want your radiation pattern, that line, to be below the ETSI mask. The ETSI mask is a reference. It lets you know what a good antenna pattern looks like. And then if you see side lobes going above the ETSI mask, then you know that those side lobes aren't necessary. There are other antennas that will perform better, that will conform with the ETSI standards. And so the ETSI mask is useful as a frame of reference. It lets you know how this antenna performs relative to industry standards. That makes it useful. Also, getting the level of detail from this, they call it an XY plot or a rectangular plot, versus the polar plot. So this is showing the polar plot representation of the antenna pattern. This is showing the rectangular representation. It's the same data. It's just represented differently, but it's not exactly the same data because the polar plot, RF Elements polar plots, only go to negative 30 dB of detail. So you've got negative 30 here, you've got 0 here. It's only showing you the detail from negative 30 to 0. The rectangular plot here, this is negative 30, this is 0 right here. So it's only showing you the detail above negative 30. It doesn't show you all the level of detail below negative 30. On cyber antennas, antenna patterns, we've got 0, negative 10, negative 20, negative 30, negative 40, negative 50, negative 60, negative 70, negative 80. So we show a whole lot more detail in these charts. RF Elements generally only shows above negative 30, so it's just right here. This level of detail gives you obviously a lot more information, but notice you can't even conform to ETSI standards unless you are showing detail down to negative, it looks like negative 48 or so right here. This is obviously way more useful than this, way more useful than some arbitrary percentage of beam efficiency.
If the radiation pattern does not stay below the mask, the antenna is not compliant, which is the case for this example. The masks are easy to understand, and to their credit, They do consider the whole 360-degree circle of a radiation pattern, but unfortunately only 2 cuts of the whole radiation pattern at 3 frequency points of the whole spectrum antenna may work in. So vast majority of the spectrum and radiation pattern is simply not included. Which is why in terms of interference suppression with networks, even these ETSI masks are really not that much of a useful parameter. So whenever you see an antenna being compliant with a particular ETSI norm, know that it does not really bring much added value in terms of noise suppression in WISP networks.
So it brings a lot of added value in terms of noise suppression in WISP networks because you can use it as a reference. So the ETSI mask is a reference value. It lets you know what you should expect from an antenna. Otherwise, it's pretty difficult to read an antenna pattern just on its own, know how that's going to compare to another vendor's antenna pattern that looks very similar, but there's small details, and it's hard to make comparisons if it's operating at different frequency points, has different grid lines and such. So the ETSI mask is very good as a reference, a frame of reference for understanding how this antenna pattern should look. And then you can see this is below ETSI class 2. There's other ETSI classes, of course. So you could have ETSI class 3, ETSI class 4, and then you would have higher levels of performance, higher standards.
At RF Elements, as a company, we are convinced about doing the right thing for the customer and the industry at the same time. So we investigated.
If they're concerned about doing the right thing for the customer and for the industry, the right thing for the customer and the industry is to provide as much detail as possible, as much education as possible on how to use that detail. What RF Elements is instead doing with their beam efficiency, they're making up an antenna parameter, calling it the most important antenna parameter, beating up their competitors, doing a very bad job explaining how this antenna parameter is useful for anything other than just saying that we have the best.
Textbooks ourselves found about beam efficiency, which is the most complete measure of side lobes out there if it's used well. When I say the most complete, I'm not just using empty overstatements or simplifications.
So with RF Elements, every day is opposite day. If he's saying he's not doing that, if he's not making empty statements and oversimplifications, then he's probably making simple statements and oversimplifications.